This one is 3.23E, and here we have a simply supported beam for which we need to find out the shear force bending moment diagram using singularity functions. So looking at the structure, there will be a reaction here R1, there will be a reaction R2 here, and due to symmetry in this beam, both of these values will be equals to P. On this beam we have only point loads, so for point loads we have singularity function which is x minus a minus 1, and the integration of this when we need it for shear force and bending moment, one integration will give us x minus a 0, and the second integration will give us x minus a to the power 1. So let's write the intensity function qx. We'll start from this side. We have p x minus 0 minus 1, second function minus p because p is acting downwards, so x minus a, which is the location, point force, that's why minus 1, again minus p, and the location for this right here is a plus b, point force, that's why minus 1. And this one last year, even if we write it there, your x minus l will never be positive for this beam, so we can ignore that part. So next step for this is from here to here we are going to integrate this to get your shear force. So I can write your Vx, so p becomes minus p x minus 0, integration gives us power 0, plus p x minus a, integration gives us 0, plus p again x minus a plus b, integration gives us 0. We can do this integration one more time to get your bending moment. So your mbx, let's flip the sign, so p x minus 0 to the power 1 minus p x minus a to the power 1 minus p x minus a plus b to the power 1. Now for this beam we have three segments that we need to analyze. Your first one is up to here, S1, S2 and S3. This is x less than equals to a, this is from a to x less than a plus b, and this is a plus b to x less than l. So let's write these three segments. So we have S1, S2 and S3. So in segment 1 we are going to have only x minus 0 giving you a positive value, meaning x minus 0 will be positive. Okay, in this segment both x minus 0 and x minus a will be positive, and in this last one x minus 0, x minus a and x minus a plus b, all of these three are going to be giving you positive arguments from inside. So now we can evaluate this. In segment 1 v1 we have to evaluate only these two, so v1 becomes minus p, x minus 0 to the power 0 will give you 1, so that's why v1 is minus p. Your mv1, p times x minus 0 to the power 1 will give you px. In segment 2 v2, now we'll have this first function and the second function also, but since we have already calculated first one, so we can take it from v1, so that is minus p, and then we can add the second part which is p times x minus a to the power 0, which gives us p. So these two put together will give you 0. In mb2 we have the first function, the value is px from here, and we can add the second function which is minus p x minus a, power 1 gives you x minus a there. So if you simplify this you get your mb2, this px and px cancels out, so you get pa from here. And the third segment you are going to have all three. Up to this point we have already calculated in v2, so v2 value is 0, so only this third term will come. So third term value is going to be p x minus a plus b to the power 0 gives us 1, so that's equals to p. Now mb3 will have your mb2 which is value pa, and the last term which is minus p x minus a plus b inside the brackets. So here if you simplify this you can actually write this as minus px, and when you combine all of this together you'll see that this p comes with 2a plus b, and if from the geometry you can see that 2a plus b is equals to l, so you can write this one as plus pl, or your mb3 is equals to p into l minus x. So now we have all these functions, so I can have an axis and I can plot this quickly. So here I have drawn one axis, so let's start plotting. Segment 1 we have to plot p1, so we get value minus p right here. Segment 2 your shear force is 0, so we maintain 0 value here, and segment 3 your value is positive p, so we go something like this. If you can combine all of this and we can shade the area here. So that's how your shear force is for this beam. Now for a bending moment, we can start from this equation. So we can evaluate this at 2 points, x equals to 0 and x equals to a. So at x equal to 0, you're going to get a value which is 0. At a, you will get value which is p times a. In the second segment, you see that we are maintaining a value of pa, so we can extend this line so that it maintains a constant value. And in the last segment, we have plx minus a. We can evaluate this at x equals to l and x equals to a plus b. Okay, if I do it at x equals to a plus b, we'll get the same value which is pa. At x equals to l, we'll get 0. So now I can combine these 2 points by a straight line. So this is how your bending moment diagram looks for this beam. So this beam right here is known as 4-point bending experimental setup, and the beauty here is that this mid portion of the beam is going through a constant bending moment without any shear force here. So that's why this is preferred for bending strength of the materials.